Hello, everyone. This is Tavares speaking. Today, in our class, we're going to remember some basic concepts about transistors and their basic circuits. Especially today, I'm going to talk about a circuit that's very used in the majority of the analogic electronic circuits, which is called polarization of the base. Basically, the circuit containing transistors that we call polarization of the base is the circuit that we have a resistor in the collector, a resistor at the base, and no resistor at the emitter. So the emitter is connected directly to the ground, okay? The idea is to, like I said, I'm going to show you an exercise, okay, in which we're going to calculate both IC, which is the current in the collector, and VCE, which is the voltage between the collector and the emitter. And during the exercise resolution, I'm going to remember some basic concepts regarding the transistor circuits, okay? So first of all, I'm going to share my screen with you. Just a second. I'll give an example of an exercise. Okay, so here we have an exercise. We have a basic circuit, which is the polarization of the base circuit that I've just talked about, in which we have a VCC, okay, a voltage that's connected directly in the resistor, the RB, which is the resistor of the base, which value is 240 kilo ohms, and at the same time it is connected to the RC, which is a resistor of the collector, okay, valuing 2.2 kilo ohms. Remembering the kilo, when we're talking about resistors, means 10 to the power of 3, so means times 1,000. So here we have 240,000 ohms, and here we have 2,200 ohms, okay? We have here just the indication of the IB, which is the current of the base, and I have here the indication of the VC, the voltage between the collector and the emitter. Here, just an indication of the IE, which is the current of the emitter, okay? In this circuit, this is a contest. This is a test that was applied in the university to be a technician in an electronics laboratory here in Brazil. And the question was, considering the circuit, this circuit, and that has a beta equals 100 and a VCE of saturation of 0.3 volts, okay? I'm putting a comma here because I first developed a video solving this exercise in Portuguese. So in Portuguese, the comma means dot and the dot means comma. But I'm going to always say dot whenever it's applicable. So here, when I put here, we don't have 2,200 kilo ohms. We have 2.2 kilo ohms, okay? But you guys are going to understand as we go through the exercise. So here, the voltage, the saturation voltage is 0.3 volts. And what they asked was, what is the current of the collector, IC, and what is the voltage between the collector and the emitter, the VCE. Here's how we do the calculation. First, one of the first equations that needs to come to your mind, when you're dealing with transistors is IC equals beta IB. IE is approximately IC, okay? They're not the exact same thing, but in 99% of the exercise that we're dealing with transistors, we can consider that the current in the emitter and the current in the collector are exactly the same, okay? So that's why we're putting here an approximation sign instead of an inequality sign. And since the problem informed us that the VCE of saturation is 0.3 volts, I'm considering that this transistor is not an ideal transistor. So I'm considering that we have a drop of voltage between the base and the emitter, which is normally 0.7 volts. Okay? If it was an ideal transistor, we could consider this as 0 volts. So first, in order to calculate the IC, we have this equation, right? Beta times IB. But we already have the beta. We do not have the IB. How do we calculate the IB? Look, we have a VCC connected here. So we have potential here is 12 volts. If we have the voltage here and here, and you do this voltage divided by this resistor, we have the IB. So if we already know that here we have 12 volts, we just need to know how many volts we have here. Remember that the voltage drop between base and emitter is 0.7. So if we have 0.7 from here to here, a drop, and here we have 0. If a drop from 0.7 happened from here to here, then from here to here, we have an increase of 0.7 volts. So we can consider that in this line here, we have 0.7 volts. In other words, if we want to calculate the IB, IB is going to be this potential minus this potential, meaning 12 volts minus 0.7 volts divided by 240 kilo ohms. Look, this equation, 12 minus 0.7 divided by 240K. IC equals beta IB. So let's substitute the value of beta here, which is 100, and the value of IB, which we have not calculated yet, but I'm going to put here the equation of the IB that we just put it above here. Okay, so we can solve this. It's very simple. 240K, we can put here, down here, 240,000. We can cut these two zeros with these two zeros, and 12 minus 0.7 equals 11.3. So IC is going to be 11.3 divided by 2,400, which if you do it in a calculator or if you can do it manually also, it's going to be something like 0.004708. The exercise required us to show a current in milliamperes. So we need to walk the comma or the dot 3 houses, 3 spots, right, to the right. So 1, 2, 3. So the current would be 4.708 milliamperes. If we want just one house after the dot, we can do an approximation and have a final result of IC equals 4.7 milliamperes. So having the IC, how do we calculate the VCE? If we go back to the circuit once again, we're going to see that now instead of looking to this side, let's look to this side. No, I'm sorry, to this side. Let's look to this side. We have 12 volts here. We have a drop of voltage of IC times RC here. We have another drop of voltage of VCE, which is exactly what we're trying to find. And then we have the final equation, which will be VCC minus RC times IC minus VCE equals 0. VCC minus ICRC minus VCE equals 0. Let's put the VCE, which is our variable of interest, on the other side of the equality sign. And then we're going to have VCE equals VCC minus ICRC. We have VCC, we have RC, in the IC we just calculated in the page above. So we have VCE equals 12 minus 4.7 times 10 to the power of minus 3. Why did I put here 10 to the power of minus 3? Because it's 4.7 milliamperes. I'm going to put the current in amperes, the resistance in ohms, and the voltage in volts. So we were going to have the final answer already in volts. I won't need to do any manipulation in order to find my final answer in volts. So 4.7 times 10 to the power of minus 3 amperes times 2.2 times 10 to the power of 3 ohms, because it's 2.2 kilo ohms, as you remember from the base circuit. Okay? So, doing base calculation, we're going to reach VCE equals 12 minus 4.7 times 2.2, because we can cut 10 to the power of minus 3 and 10 to the power of 3, because as you know, when I have two numbers, okay, two powers, in which we have the same base but different numbers in the powers here, we can just maintain the base and sum the powers. So 10 minus 3 plus 3 equals 10 to the power of 0, which, as you all know, 10 to anything to the power of 0 equals 1. So we have 12 minus 4.7 times 2.2, which is 12 minus 10.34, which is 1.66. And if we want to round to just one house after the dot, it's going to be 1.7 volts. So we have the final answer as IC equals 4.7 milliamperes and VCE 1.7 volts. Again, bear with me, I should have rewritten this using dots instead of comma because of the English version, but I think I was able to cover any possible doubts regarding this. Okay, thank you very much for watching this. Please subscribe to the channel if you want to receive more tips and more exercise resolutions, as well as subjects explanations. Okay, and give your like. It's very important for us to continue our work. Thank you very much and have a nice day.